ಸ್ಟಾರ್ಟ್ ಮಾಡಿದ ಮೇಡಮ್.
ಫೋರಿಗೆ ಸ್ಟಾರ್ಟ್ ಮಾಡುವ ಸರ್. 4ಗೆ ಸ್ಟಾರ್ಟ್ ಮಾಡುವ ಸರ್.
ಓಕೆ ಓಕೆ. PPT ಶೇರ್ ಮಾಡ್ಕೊಳ್ಳಿ.
Yes sir. You can start.
PPT ಶೇರ್ ಮಾಡ್ಕೊಳ್ಳಿ. It's visible ma'am, ಅದು ಫುಲ್ ಸ್ಕ್ರೀನ್ ಮಾಡ್ಕೊಳ್ಳಿ.
ಫುಲ್ ಸ್ಕ್ರೀನ್ ಮಾಡಿದಲ್ಲ?
ಮಿನಿಮಮ್ ಸ್ಕ್ರೀನ್ ಇದೆ, ಫುಲ್ ಸ್ಕ್ರೀನ್ ಮಾಡ್ಕೊಳ್ಳಿ. Yes, ma'am.
Okay, sir.
So start ಮಾಡಿದೆ ಮ್ಯಾಮ್.
ಆಯ್ತು ಸರ್.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. ಇಂದಿನ ವಿಜ್ಞಾನ ಪ್ರತಿಭಾ ಶೋಧ ಯೋಜನೆಯ 59ನೇ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಡಾಕ್ಟರ್ ಗೀತಾ ಪಿಂಟೋ ಮೇಡಮ್ ರವರನ್ನ ಈ ಒಂದು ವೇದಿಕೆಗೆ ಸ್ವಾಗತ ಮಾಡ್ತಾ ಇದ್ದೀನಿ. ವೆಲ್ಕಮ್ ಟು ಯು ಮ್ಯಾಮ್.
ಥ್ಯಾಂಕ್ ಯು ಸರ್.
And I also welcome to all the attendees, lecturers and teachers. Welcome to my colleagues. And I also welcome to all the participants. So, ಕಳೆದ ತರಗತಿಯಲ್ಲಿ ಡಾಕ್ಟರ್ ಗೀತಾ ಪಿಂಟೋ ಅವ್ರ ಬಗ್ಗೆ ಒಂದು ಕಿರು ಪರಿಚಯನ ಮಾಡಿಕೊಟ್ಟಿದ್ದೀನಿ. ಕಾಲಾವಕಾಶ ಕಡಿಮೆ ಇರುವ ಕಾರಣ ಸೊ ಈ ಒಂದು ವೇದಿಕೆಯನ್ನ ಡಾಕ್ಟರ್ ಪಿಂಟೋ ಮೇಡಮ್ ಅವ್ರಿಗೆ ಬಿಟ್ಕೊಡೋಕೆ ನಾನು ಇಷ್ಟಪಡ್ತಾ ಇದ್ದೀನಿ. ಓವರ್ ಟು ಯು ಮ್ಯಾಮ್.
ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಗುಡ್
ಸೊ
ಈವ್ನಿಂಗ್.
ವಿದ್ಯಾರ್ಥಿಗಳೇ, ರಿಸೋರ್ಸ್ ಪರ್ಸನ್ ಜೊತೆ ನಿಮ್ಗೆ ಏನೇ ಡೌಟ್ಸ್ ಇದ್ರು ಕೂಡ ದಯವಿಟ್ಟು ಕ್ವಶನ್ಸ್ ಆಗಲಿ ಏನೇ ಆಗಲಿ ನೀವು ಕೇಳಬೇಕಂದ್ರೆ ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲೂ ಕೂಡ ಕೇಳಿ ಅವ್ರ ಜೊತೆ ಇಂಟ್ರಾಕ್ಷನ್ ಆಗಿ ಅಂತ ನಮ್ಮ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ತಿಳಿಸ್ತಾ ಇದ್ದೀನಿ. ಸೊ ಓವರ್ ಟು ಯು ಮ್ಯಾಮ್.
Okay. Good evening students. Today my talk is crystal field theory. That is a part of coordination chemistry. Coordination chemistry, there are three theories: valence bond theory, then crystal field theory, then molecular orbital theory. So we will be studying crystal field theory. So before starting crystal field theory, now the contents of crystal field theory are: before starting crystal field theory, we will discuss the limitations of valence bond theory. We should know what is valence bond theory and the limitations of valence bond theory, why we are going for crystal field theory. So crystal field theory ಕಲಿಯುವ ಮುಂಚೆ ವ್ಯಾಲೆನ್ಸ್ ಬಾಂಡ್ ಥಿಯರಿ ಅಂದ್ರೆ ಏನು ಮತ್ತೆ ಅದರ ಲಿಮಿಟೇಷನ್ಸ್ ಗಳ ಬಗ್ಗೆ ಸ್ವಲ್ಪ ನೋಡ್ಕೊಳ್ಳೋಣ. ಮತ್ತೆ how crystal field theory is applied to octahedral complexes and the square planar and the tetrahedral complexes. So three complexes we will be studying: octahedral complexes, tetrahedral complexes and square planar complexes. Then we will be studying the applications of crystal field theory. So the uses of studying crystal field theory. Now valence bond theory, when we study, I said there are four theories, that is valence bond theory, crystal field theory, ligand field theory and molecular orbital theory, and we will be studying crystal field theory. Now what is, first of all, before studying the valence bond theory, what is valence bond theory? ಈಗ valence bond theory ಗೂ crystal field theory ಗೂ ವ್ಯತ್ಯಾಸ ಏನು ಅಂತ. ವ್ಯಾಲೆನ್ಸ್ ಬಾಂಡ್ ಥಿಯರಿ ನೋಡ್ಲಿಕ್ಕೆ ಹೋದ್ರೆ ನಾವು ಅದರಲ್ಲಿ ಇಂಪಾರ್ಟೆಂಟ್ ಥಿಂಗ್ ಇಸ್ ದ ವ್ಯಾಲೆನ್ಸ್ ಬಾಂಡ್ ಥಿಯರಿ mainly focuses on the bond between the ligands and the metal. Ligand ಮತ್ತೆ ಮೆಟಲ್ ಮಧ್ಯೆ ಬಾಂಡ್ ಕೋಆರ್ಡಿನೇಟ್ ಬಾಂಡ್ ಆಗಿರ್ತದೆ. Whereas in crystal field theory, the type of bond is ionic type of bond. So in valence bond theory, the bond between the metal ion and the ligand is coordinate bond. That means you know that coordinate bond is formed by sharing of the electrons between the two atoms. Sharing of the electrons between the two atoms, but sharing is contributed by only one ligand. Sharing is contributed by the ligand, not the metal here. So as we have studied valence bond theory, we will see why the valence bond theory is failure there. ಯಾಕೆ ವ್ಯಾಲೆನ್ಸ್ ಬಾಂಡ್ ಥಿಯರಿ ಅಷ್ಟರ ಮಟ್ಟಿಗೆ ಸಕ್ಸಸ್ ಆಗಲಿಲ್ಲ, ಯಾಕೆ ನಾವು ಕ್ರಿಸ್ಟಲ್ ಫೀಲ್ಡ್ ಥಿಯರಿಯನ್ನು ಕಲಿಬೇಕು? ಸೊ ದ ಲಿಮಿಟೇಷನ್ಸ್ ಆಫ್ ವ್ಯಾಲೆನ್ಸ್ ಬಾಂಡ್ ಥಿಯರಿ ಆರ್, valence bond theory doesn't explain why copper ions are formed distorted octahedral complexes. So when copper forms complexes, you know that When copper forms octahedral complex, sorry, when copper forms octahedral complexes, it forms distorted octahedral complex. Distorted octahedral complex means all the six ligands are not of same size. All the six ligands are not of same size. One second. See here, octahedral octahedral complex, that is, if we are writing octahedral complex, six, there are six ligand. When it is forming the complex, all the six ligands are not of same length. Distorted octahedral complex means maybe along the z axis the ligands are elongated, or x and y axis the ligands are elongated. So this valence bond theory doesn't explain what is the reason for forming distorted octahedral complexes. It is not the regular octahedral complex. So valence bond theory doesn't explain. Then one more limitation is, if you take cupramonium complex, that is tetrahedral complex, four ligands, when there are four ligands surrounded by the central metal ion, there are chances of forming square planar complexes as well as tetrahedral complexes. Tetrahedral complex. Now, cupramonium complex, when it is formed, it uses dsp2 hybrid orbitals. You know that when square planar complexes are formed, it will be using dsp2 hybridized orbitals, and tetrahedral complexes are formed, it will be using sp3 hybrid orbitals. Now, here in this particular complex, even though there is one s and two p orbit, three p orbitals free there, it doesn't form ಇದು tetrahedral complex form ಮಾಡಲ್ಲ. So it doesn't form tetrahedral complex. The reason behind the formation of square planar complexes is not explained by valence bond theory. So why copper forms square planar complexes? Why it is utilizing the sp2 hybrid orbitals? Why can't it utilize sp3 hybrid orbitals? sp3 hybrid orbital ಅಲ್ಲಿ free ಇದ್ರೂನು ಇಲ್ಲಿ for example copper electronic configuration ನಾವು ಬರೆದ್ರೆ copper, it is argon 3d 9 4s2. So when it is forming copper plus 2, it is argon 3d, we can write 3d10 4s1, and the three electrons are removed there, that is copper plus 2 3d9 and 4s2. So these two electrons can be removed when copper plus 2 ion is formed, and there is s orbital which is free, and we can write 4p orbital free. So there are four s orbital and four p orbitals which are free there, but still it doesn't utilize the s orbital and 3p orbital. It doesn't utilize, and it will not form sp3 hybrid orbitals for the formation of tetrahedral complexes. So this is the drawback, and there are many drawbacks. Then valence band theory, it does not explain satisfactorily why some complexes of a metal in a particular oxidation state form high spin complex, and in some particular oxidation state it forms low spin complex. So this valence bond theory doesn't explain why the particular oxidation state form high spin, sometimes it forms high spin complex, sometimes it forms low spin complex. So this valence bond theory doesn't explain what is the reason for the formation of high spin as well as low spin complexes. So the drawback is fulfilled by the crystal field theory. Crystal field theory is given by these two scientists, Brett and Van Vleck. In 1935, they have given this theory. So the question is now, why the crystal field theory? Why the name crystal? From where the crystal name came. So field theory, okay, the ligand field is influencing on the metal ion. Why the name crystal? So the name crystal refers to the regular geometric arrangement. If you can see here, it is the regular geometric arrangement. So just like crystal. So you know that in crystal, each unit cell is joined with other unit cell in three-dimensional space. Over the three-dimensional space, all the unit cells are joined together to form a geometric arrangement or regular pattern. You know that in crystals there is a regular arrangement of unit cells. Whereas here also in crystal field theory also, it is referred as crystal. It is mainly because ligands are surrounding the central metal ion. Ligands are surrounding the central metal ion. See, the ligands are surrounding the central metal ion with the regular geometric arrangement. The arrangement is similar to that of the crystal lattice. The arrangement of unit cells in the three-dimensional space is compared with the arrangement of ligands around the central metal ion. The geometric arrangement is exactly similar to the arrangement of unit cell in the crystal. That is why the name crystal. So crystal field theory, the name crystal is derived from the pattern. Pattern means it is a regular geometric pattern of the ligands around the central metal ion. There is a regular geometric pattern will be there. So that is why the name crystal field theory. Now let us see the assumptions of crystal field theory and how it is different from your valence bond theory. Now valence bond theory, if you are talking about, it is the name itself suggests the valence electrons are involved. If you are considering the electronic configuration, when you know that in valence bond theory, the coordinate bond is formed. When the coordinate bond is formed between the metal and the ligand, in valence bond theory, the coordination bond is formed by the ligand and the metal ion, where the electrons are contributed by the ligand. Whereas here, the central metal cation is surrounded by the ligands, which cation one or more lone pairs of the electrons. So central metal ion is surrounded by ligands which contain one or more lone pair of the electrons. So you know that ligands. What is ligands? What are ligands? Ligands are the negatively charged entity. It can be ion, negatively charged ion, and if it is a neutral molecule like water, ammonia, etc., they must contain the lone pair of the electrons. So that is the meaning of the ligand. So ligand can approach the metal ion, and during the valence bond theory we explain valence bond theory. It is formed, the bond is formed by involving the valence electron. What do you mean by valence electrons? What do you mean by valence electrons? If the students are there, can answer. What do you mean by valence electrons? I said valence bond theory involves the bond between metal and the ligands where valence electrons are involved. Valence electrons are involved. Outermost electrons are called valence electrons. Outermost electrons are called valence electrons. That is why valence bond theory. So here, ligands which contain one or more lone pair of electrons. That is the first assumption. So central metal cation is surrounded by ligands which contain one or more lone pair of electrons. Then the second assumption, the ligands maybe F minus, Cl minus, Cn minus, Br minus, I minus. So any negatively charged ions, if you take F minus, Cl minus, Br minus, I minus, Cn minus, etc. if you take, or oxalate ion is a bidentate ligand, and oxide ion O2 minus, all are having negative charges. They are regarded as negative point charges. And some ligands like water, ammonia, and the organic ligands like pyridine, then your some of the organic ligands, they are having lone pair of electrons. Some of the organic ligands contain lone pair of lone pair of electrons. For example, EDTA is the best ligand. It is the hexadentate ligand. So here in EDTA, nitrogen atoms contain lone pair of electrons, are regarded as point dipoles. So any ligand which contains lone pair of electrons, they are regarded as point dipoles. Point dipoles ಅಂತ ಕರಿತೇವೆ. Any ligand which contains negative charges, fluoride, chloride, bromide, iodide, cyanide, oxalate. So ಈ negative ಚಾರ್ಜ್ಗಳ ಲಿಗ್ಯಾಂಡ್ ಅನ್ನು ನೆಗೆಟಿವ್ ಪಾಯಿಂಟ್ ಚಾರ್ಜಸ್ ಅಂತ ಕರೀತೇವೆ. ಸೊ ನೆಗೆಟಿವ್ಲಿ ಚಾರ್ಜ್ ions are called negative point charges, and the neutral molecules containing lone pair of electrons, which are ligands, are considered as point dipoles. So the third assumption is the metal ion and ligands don't mix their orbitals. So metal ion ಮತ್ತೆ ligand ಅವರ ಅವುಗಳ ಆರ್ಬಿಟಲ್ಗಳನ್ನು ಮಿಕ್ಸ್ ಮಾಡಲ್ಲ or share ಮಾಡಲ್ಲ. You know that sharing the electrons, what do you mean by sharing the electrons? When the electrons in the orbitals are shared, the bond formed is coordinate bond or covalent bond. Whereas here in crystal field theory, they are not sharing the electrons. Then what? If not sharing, then what? What type of bonds? ಯಾವ type of bond form ಆಗ್ತದೆ? ಶೇರ್ ಮಾಡುವ ಬಾಂಡ್ ಅಲ್ಲದಿದ್ರೆ, ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಅನ್ನು ಶೇರ್ ಮಾಡಿ ಉಂಟಾಗುವ ಬಾಂಡ್ ಅನ್ನು ಕೋಆರ್ಡಿನೇಟ್ ಬಾಂಡ್ ಅಥವಾ ಕೋವೆಲೆಂಟ್ ಬಾಂಡ್ ಅಂತ ಹೇಳ್ತೇವೆ. ಈಗ ಶೇರ್ ಮಾಡದೆ ಉಂಟಾಗುವ ಬಾಂಡ್ ಅನ್ನು ಅಯಾನಿಕ್ ಬಾಂಡ್ ಅಂತ ಹೇಳ್ತೇವೆ. ಆಗ ಶೇರ್ ಮಾಡದೇ ಇರುವ ಬಾಂಡ್ ಅಯಾನಿಕ್ ಬಾಂಡ್. ಸೊ what is ionic bond? Can you tell me what is ionic bond? They don't involve the sharing of the electrons or mixing up of the orbitals are not there in ionic bond. So what are ionic bond then? It is the bond formed between the two atoms by transfer of electrons. electrons, transfer of electrons from one atom to other, or when the electron is transferred from one atom to other, there will be charge developed, one which is transferring electron positively charged, one which is accepting the electron which is negatively charged. So there are two dipoles formed, positive as well as negative dipoles are formed. So when positive dipole is formed, there are positive and negative dipole. So the attraction between these two charges, positive charge and the negative charge, is known as electrostatic force of attraction, and the bond formed is called ionic bond. So I repeat the assumptions of crystal field theory. The first assumption is the central metal cation is surrounded by the ligands. Ligands may contain one or more lone pair of the electrons, or it can contain a neutral, it can contain negatively charged ions. Can be lone pair like water, ammonia, etc. If you consider, it can contain a lone pair, or if you consider halide, cyanide, or nitrate, etc., it doesn't contain lone pair of the electrons, it contains negative charge. So the ionic ligands, negatively charged ligand, is considered as negative point charges, and the molecules which are having lone pair of the electrons, which are considered as ligand, and it is the name of that is point dipoles. The metal ion and the ligand don't mix up their orbital just in, as you have seen in valence bond theory, they are mixing up their orbitals. Here they are not mixing up their orbitals. And the fourth assumption is the bond formed between the metal and the ligand is purely ionic. So these are the four assumptions by crystal field theory. Now we have to apply this crystal field. ಈ crystal field theoryಯನ್ನು ಆಕ್ಟಾಹೆಡ್ರಲ್ ಕಾಂಪ್ಲೆಕ್ಸ್ ಮತ್ತೆ ಟೆಟ್ರಾಹೆಡ್ರಲ್ ಕಾಂಪ್ಲೆಕ್ಸ್ ಮತ್ತೆ ಸ್ಕ್ವೇರ್ ಪ್ಲೇನಾರ್ ಕಾಂಪ್ಲೆಕ್ಸ್ಗೆ ಅಪ್ಲೈ ಮಾಡಲಿಕ್ಕೆ ಉಂಟು. ಈಗ ಫಸ್ಟ್ ಆಫ್ ಆಲ್ ಆಕ್ಟಾಹೆಡ್ರಲ್ ಕಾಂಪ್ಲೆಕ್ಸಸ್. So what do you mean by octahedral complexes? How it is formed? Octahedral complex is formed by having the metal ion at the center, having the metal ion at the center here, metal ion Mn plus, and when it is surrounded by six ligands, L1, L2, L3, L4, L5, and L6. So this complex is formed by sharing six ligands. So it is the attraction between the, I said the fourth assumption says crystal field theory assumes that the bond between the ligands and the metal is purely electrostatic, or it is purely ionic. That means there is the attraction between the positively charged central metal ion and the negatively charged ligand. So when they are attracting, the octahedral complex is formed there. Octahedral complex is formed by mere attraction between the positive charge of the metal and the negative charge of the ligand. So you know that metals are electropositive, alva. All metals are electropositive in nature, and ligands are having negative charges. Some of the ligands are having negative charges like halides, and some of the ligands are having lone pair of the electrons. And here when we discuss octa means it is not 8 ligand, it is 6 ligands, but the geometry when you see the octahedral complexes geometry, when you see there are 6 ligands and there are 8 faces. When 6 ligands are joining and form octahedral complexes, there are 8 faces for that complex particular geometry. 8 faces are there. So if you consider my hand, and you know that there are 4 ligands on the plane, and one ligand up and one ligand down here. So as there are 6 ligands and the faces, one face here, two face, 3 phase, 4 phase. Similarly, down 4 phases are there. 8 phases are there. That is why the name octahedral complex. Now, when we study crystal field theory, or when we apply crystal field theory to octahedral complexes, how the metal ion, the central metal ion, the valence orbitals, which are the valence orbital, it can be s orbital, p orbital, or the d orbital. Now, one more special thing about crystal field theory is it is considering the d orbitals only. It will be considering only the d orbital. Now, in the case of free metal ion, you know that all the 5d orbitals are degenerate. What do you mean by degenerate? Degenerate means all the 5d orbitals are of same energy. So, which are the 5d orbitals? It is dxy, dxz, dyz, dx square minus y square, and dz square. So, all the 5d orbitals are having same energy if it is free metal ion. But if you consider the octahedral complex, that means when the 6 ligands are approaching the central metal ion, you know that 6 ligands form the octahedral complexes. When the 6 ligands are surrounded by the central metal ion, it will be occupying the 6 corners of the octahedron. So when the central metal cation is placed at the center of the octahedron and is surrounded by 6 ligands which resides at the 6 corners of the octahedron. So in the octahedral complex, we can consider the central metal ion and the 6. This is the three-dimensional picture, and the 6 ligands are residing at the 6 corners of the octahedron. Now, when the ligands, 6 ligands are approaching the central metal ion, it can see the 5 metal d orbitals of different shape. You know that dx, dy, dxy, and dxz. They are of different shape, and they are of different energy. See here, dyz, dxy, and dxz, they occupy in between the axis. You have to remember that. And dx square minus y square and dz square orbitals, they are on the axis. You can see dx square minus y square is between x and on the the x square minus y square orbital is on x axis and on the y axis, the two lobes of the double dumbbell, isn't it? D orbital is double dumbbell, and the two lobes are on the x axis and on the y axis. You can see here, red colored one is on the y axis and the blue color is on the x axis. And dz square orbital, if you see, it is, the name itself suggests z square, means on the z orbital only the two lobes are occupied. One z orbital you can see here, z axis you can see here, one lobe, and here blue color another lobe. On the z axis only there are two lobes of the d orbitals are occupied. Now here dyz, if you see, the d orbital is occupying between y and z axis. Dxy, the lobes are occupying between x and y axis, between the x and y axis. And dxz, if you see, the lobes are occupying between x and z axis, between the x and z axis. Now, when you compare all the 5 orbitals, the upper one, 3 orbitals are in between the axis, and the lower 2 orbitals, that is dx square minus y square and dz square, they are on the axis. Now, if I ask a question, when the ligands are approaching the central metal ion, whether the ligand electrons experience the same type of repulsion. You know that the central metal ion, when they are surrounded by ligands, central metal ion also is having some electrons, and the ligands are also having some electrons. The metal d orbitals are having some electrons, and the ligands are having some electrons. When they interact, there will be repulsion, recursion, akarshana, because electrons of the central metal ion is approaching the ligands of this ligands. The six ligands are there. The electrons of the ligands are approaching the central metal ion containing electrons in the d orbital. So electrons and electrons repulsion is taking place. When they are repelling, my question is now, when there are 5d orbitals, dx, dyz, dxz, dxz, xy, dxz, dx square minus y square, and dz square. When there are 5d orbitals, whether the repulsion or recursion, whether it is same with the ligands or different. Free metal ion, it is free metal ion containing electrons. When free metal ion, it contains electrons. When the ligands are approaching, ligands are also containing electrons. So when the complex is formed, octahedral complex of this nature is formed. This is the octahedral complex, central metal ion, having the metal d orbitals. When the ligand, six ligands are approaching, they are also having electron. When they come near to the metal ion, whether the repulsion is of same nature or different nature. Same nature or different nature. It is of different nature, because here this dyz, dxy, and dxz orbital, they are of they are in between the orbitals, in between the axis. These three orbitals are in between the axis, whereas dx square minus y square and dz square are along the axis. Why? The energy experienced by the ligand between the metal d orbitals are not same, because you know that when the octahedral complex is formed, you can see here this ligand, I will designate it as L2, L3, L5, and L6. They are in one plane, isn't it? If I join, they are planar. They are on the plane. And this is one above and one below. Now, if you see all the ligands, if I consider this L6 and L3 ligands, if I consider, this is, if I consider this as x-axis and this as y-axis and this as z-axis, if I consider, you can see that this x-axis and y-axis and the z-axis, the ligands are also coming along the x-axis, y-axis, and z-axis. So when you form octahedral complex, the shape of the octahedral complex, if you consider, all the ligands are approached towards the metal ion and they are on the axis. This ligand also on the axis. This ligand is also on the axis. These ligands are also on the axis. X, Y, and Z axis. They are on the X, Y, and Z axis. So you can see that out of the five orbitals, which are the two sets which are on the axis, this, isn't it? Dx square minus y square and dz square orbitals are on the axis. So whichever metal orbitals which are on the axis, they experience more repulsion compared to the orbitals which are in between the axis. See, these are in between the axis. Now ಇಲ್ಲಿ ಲಿಗ್ಯಾಂಡ್ ಬಂದ್ರೆ ಈ ತ್ರೀ ಈ ಮೂರು ಆರ್ಬಿಟಲ್ಗಳ ಹತ್ರ ಲಿಗ್ಯಾಂಡ್ ಬಂದ್ರೆ ಅವುಗಳ ವಿಕರ್ಷಣೆ ಕಡಿಮೆ. ಯಾಕೆಂತ ಹೇಳಿದ್ರೆ ಅವುಗಳು ಆಕ್ಸಿಸ್ ಅಲ್ಲಿಲ್ಲ, ಅವುಗಳು ಮಧ್ಯದಲ್ಲಿದೆ, ಆಕ್ಸಿಸ್ನ ಮಧ್ಯದಲ್ಲಿದೆ. ಡಿ ಎಕ್ಸ್ ವೈ ತಗೊಂಡ್ರೆ ಎಕ್ಸ್ ಮತ್ತೆ ವೈ ಆಕ್ಸಿಸ್ನ ನಡುವೆ ಇದೆ. ಡಿ ವೈ ಝೆಡ್ ತಗೊಂಡ್ರೆ ಇದು ವೈ ಮತ್ತೆ ಝೆಡ್ಡಿನ ನಡುವೆ ಇದೆ. ಡಿ ಎಕ್ಸ್ ಝೆಡ್ ತಗೊಂಡ್ರೆ ಎಕ್ಸ್ ಮತ್ತೆ ಝೆಡ್ಡಿನ ನಡುವೆ ಇದೆ. ಬಟ್ ಈ ಎರಡು ಆರ್ಬಿಟಲ್ directly on the axis, x axis, here x and y axis, here z axis. Therefore ligands are having more repulsion with the metal electrons having these two sets of orbitals. So when there is, you know that when there is a repulsion aguvaga energy ಜಾಸ್ತಿ ಆಗ್ತದೆ, isn't it? So here repulsion is less because these three orbitals are in between the axis and these two orbitals are along the axis. So they experience different energy. As you can see here, the free metal ion, all the 5d orbitals are of same energy. When they come in contact with the ligands, there will be repulsion. All the 5d orbitals are hypothetically raised, and when whether they are equally raised, no. Which are the two orbitals which are having more repulsion among the five? These two, isn't it? These two are having more repulsion. So when they are, why they are having more repulsion? Because they are on the axis. So axis orbitals are experiencing more repulsion. Why axis orbitals are experiencing more repulsion? Because all the six ligands are on the axis, x-axis, y-axis and z-axis. When they are on the axis, these two orbitals are experiencing more repulsion and they are having more energy. Their energy levels are raised. And similarly, and these three orbitals, they are in between the axis. They are experiencing less repulsion. Why they are experiencing less repulsion? Because they are not coming in directly contact with the ligands. So they are having less repulsion. Their energy is lowered. So earlier hypothetically we have assumed that all the 5d orbitals are of same energy. Now when all the 5d orbitals are approaching, when the ligands are approaching all the 5 metal d orbitals, there will be repulsion between the electrons of the metal and the electrons of the ligand. Now among the 5 sets of the orbitals, these two sets experience more repulsion. Why these two sets experience more repulsion? Because they are on the axis. Ligands are also on the axis. Ligands, to form octahedral complex, ligands must be x, y and z direction. You have seen the octahedral complex shape. It will be on the x, y and the z axis. So they will be experiencing more repulsion and other three will be experiencing less repulsion. And these three orbitals are split, crystal field splitting. It is the splitting up of the 5 degenerate orbital. These are 5 degenerate. What do you mean by degenerate? Having same energy. They split up into two sets of orbitals of different energy is called crystal field splitting. This is called crystal field splitting. This diagram is of crystal field splitting of octahedral complex. So
ಕ್ಯಾಮ್ರಾ ಸ್ವಲ್ಪ ಹೈಟ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಕ್ಯಾಮ್ರಾ ನಿಮ್ಗೆ ಕಣ್ಣು ಕಾಣಿಸ್ತಾ ಇಲ್ಲ. ಇಟ್ಸ್ ಓಕೆ ಸರ್.
crystal field and crystal field stabilization energy. So it is the lowering in the energy of a transition metal ion in a given ligand environment due to the crystal field effect. So it is some energy is lowered. You can see here the amount of energy lowered is 2 by 5, that is minus zero point 0.4 delta naught energy is lowered, and it is 3 by 5 is equal to zero point 0.6 delta naught is increased. So as it raises, this energy is raised and it is indicated by plus sign. As the energy of these three orbitals are lowered, it is indicated by the negative sign, and it is calculated to be minus 4 delta naught, or it is also, if you convert it into whole number, it can be considered as 4 dq, and this can be considered as 6 dq. And you know that the crystal field stabilization energy is calculated to be 6 dq minus of minus 4 dq. So it will be 10 dq. Total of 10 dq energy is. So total energy, crystal field stabilization energy is here, if you consider, it is delta naught, that is zero point 0.6 delta naught minus of minus zero point 0.4 delta naught, or it is 6 dq minus of minus, it is minus 4 dq, it is total of 10 dq energy. Now crystal field theory applied to tetrahedral complexes. When you consider tetrahedral complexes, there are only four ligands. You can see here L1, L2, L3, and L4. So these four ligands, when you consider, these four ligands are are in the alternate corners of the cube. You can see here cube. The cube can't repeat. So we have studied octahedral complexes. Now tetrahedral complex. Tetrahedral complex, we are having only four ligands. And how tetrahedron is imagined? Octahedral, it was very easy. If you consider a plane, one up, four ligands on the plane, and one above and one below. Whereas tetrahedral complex, when you consider, you have to consider a cube, and you have to consider alternate corners, the ligand. So there are 8 corners for a cube, and alternate corners ligands are placed. L1 ligand, then L2 ligand, then L3 ligand, then L4 ligand. So you can see here these three are in one plane, and this is, so tetrahedron you can imagine. So how the crystal field splitting in tetrahedral complexes is taken is, now you have to consider the central free metal ion. In free metal ion, all the 5d orbitals are degenerate. What do you mean by degenerate? All the 5d orbitals are of same energy. Now, if you consider tetrahedral complex, there are four ligands, and tetrahedral complex is written as Ml4 and N plus. The charge can vary based on the metal ion oxidation state. The central metal cation is placed at the center of the tetrahedron. See here, it is placed at the center of the tetrahedron and is surrounded by four ligands. See, 1, 2, 3, 4 ligands. It is surrounded at the alternate corners of the cube. Here I have kept, here I have not kept, here I have kept, here I have not kept. Here ಇಲ್ಲಿದೆ ಮತ್ತು ಇಲ್ಲಿ ಇಲ್ಲ, ಇಲ್ಲಿದೆ. So all the 8 corners are not occupied, whereas alternate corner ಒಂದು ಬಿಟ್ಟು ಒಂದು corners, if they occupy, they form tetrahedral complex. So all the four ligands approaching Mn plus, that is central metal ion, are lying in between the three x, y, z axis. So as I said, in octahedral complexes, the ligands are approaching along the x-axis, y-axis, and z-axis. Whereas here it is different. The ligands, when they are approaching the electrons, you know that it is obvious that the electrons of the metal d orbitals are repelled by the negative point charges or the dipoles of the ligands. The repulsion will raise the energy of the metal d orbitals, you know that, and none of the metal d orbitals are in the direction of the ligands. If you see here, see, x-axis is here, y-axis is here, z-axis is there. On the x-axis, there is no ligand. On the y-axis, there is no ligand, isn't it? If I draw here, see, here there is a ligand, here there is a ligand, here there is a ligand, here there is a ligand. Whereas x-axis there is no ligand, y-axis there is no ligand, z-axis there is no ligand. So that means dx square minus y square and dz square orbitals of the central metal ion experiences least repulsion. Earlier case, dx square minus y square orbital and dz square orbital, they are called as Eg orbitals. They are experiencing more repulsion, isn't it? Because the ligands are on the axis. Whereas here, none of the ligands are on the axis. So dx square minus y square and dz square, that is E orbitals. Here we are not calling them as Eg because there is no center of symmetry for the tetrahedral complex. So the E orbitals are not along the ligand. So ligands are not in a direction with the E orbitals. Which are the E orbitals? Students, can you tell me the E orbital, E set of orbitals? E set of orbitals are dx square minus y square, is one orbital, and dz square orbital. So they are experiencing least energy. Earlier case, in octahedral complexes, they are experiencing more energy because their repulsion is more. They are directly coming in contact with the ligands. Direct ಆಗಿ ಕಾಂಟ್ಯಾಕ್ಟ್ ಆಗ್ತದೆ ಆಕ್ಟಾಹೆಡ್ರಲ್ ಕಾಂಪ್ಲೆಕ್ಸ್ ಅಲ್ಲಿ. ಟೆಟ್ರಾಹೆಡ್ರಲ್ ಕಾಂಪ್ಲೆಕ್ಸ್ ಅಲ್ಲಿ ಡೈರೆಕ್ಟ್ ಕಾಂಟ್ಯಾಕ್ಟ್ ಇಲ್ಲ, ಲಿಗ್ಯಾಂಡ್ ಮತ್ತೆ ಮೆಟಲ್ಗೆ ಡೈರೆಕ್ಟ್ ಕಾಂಟ್ಯಾಕ್ಟ್ ಆಕ್ಸಿಸ್ ಅಲ್ಲಿ ಇಲ್ಲ. ಆದ ಕಾರಣ ಆಕ್ಸಿಸ್ ಆರ್ಬಿಟಲ್ಸ್ ಇದು ಎನರ್ಜಿ ತುಂಬಾ ಕಡಿಮೆ. So see the look at the splitting here. The 5d orbitals, let us assume that they are all raised, hypothetically raised to a higher energy level, but when they come in contact with the ligands, four ligands, now the ligands which are approaching the central metal ion are dxy, dxz, and dyz, exactly opposite of the octahedral. The ligands which are having least repulsion is dx square minus y square and dz square orbital. So E. So these three orbital dxy, dxz, and dyz you can see here, isn't it? This is the x-axis and this is the z-axis. If you see here, the one ligand which is in between the dxz axis having repulsion, it is little near, ಸ್ವಲ್ಪ ಹತ್ತಿರ ಇದೆ ಈ ಲಿಗ್ಯಾಂಡ್ ಮತ್ತೆ ಡಿ ಎಕ್ಸ್ ಝೆಡ್ ಆರ್ಬಿಟಲ್ ಇದ್ದು, ಈ ಲಿಗ್ಯಾಂಡ್ ಇದು ಎಲೆಕ್ಟ್ರಾನ್ ಮತ್ತೆ ಈ ಡಿ ಎಕ್ಸ್ ಝೆಡ್ ಆರ್ಬಿಟಲ್ ಇದ್ದು ಎಲೆಕ್ಟ್ರಾನ್ is nearby, therefore repulsion is there. So that is why these orbitals, in between orbitals of the metal, is raised. The energy is raised. E orbital's energy is lowered. How much? It is lowered by 3 by 5. 3 by 5 is equal to minus zero point 0.6 delta T. And how much it is raised? Can you tell me? It is 2 by 5. 2 by 5 it is raised, that is zero point 0.4 delta T. So total energy is delta T, and if you compare with the octahedral complex, it is half of the splitting energy is less. Splitting energy, if the octahedral complex splitting energy is this much, octahedral complex splitting energy is represented by delta naught, and tetrahedral complex, it is given by delta T small is half. So it is minus 0.45 delta naught. It is not exactly half. It is 0.45 is near to zero point 0.5. So it is half of the delta naught splitting. So if I ask the question why it is the splitting energy is half of that of the octahedral complex, because here all the ligands in tetrahedral complexes are only 4, whereas in octahedral complexes there are 6 ligands. So these 4 ligands repulsion is less compared to 6 ligand. Therefore the tetrahedral splitting parameter is nearly half of that of the octahedral complex. Now, crystal field theory applied to square planar complex. So, square planar complexes, when we consider, first we have to consider the octahedral complexes. Then we have to consider tetragonal. That means when the ligands along the z-axis is elongated, what happens? That means when they are elongated, the metal and the ligand bond is weak. That means the metal orbitals, whichever, this is the z-axis, isn't it? Whichever is on the z-axis, its energy is lower. So here dxy, dxz and dyz, z orbital energy is lower and xy orbital energy is increased. This is tetragonal or distorted octahedral. What do you mean by distorted octahedral? All the 6 bond lengths are not equal. Here z axis, the bond length is elongated, means the attraction between the metal and ligand is weaker, means there will be less repulsion. When there is less repulsion between the metal ion and the ligands approaching along the z axis, less repulsion means less energy. That is what it is shown. So all the z containing orbitals are coming down. Now, what is square planar complexes? The z-axis ligands, I said, the bond between metal and ligand along the z-axis is weaker and it forms distorted octahedral. Finally, when it is very weak, these two bonds are destroyed or they become very weak and they will be vanished. So as the z bond is vanished, that is z direction, two bonds are vanished, you will be getting square planar complexes. What do you mean by square planar complexes? There will be only 4 ligands approaching along the x-axis and y-axis. Z-axis there won't be any ligands. So when it forms distorted octahedral to square planar complexes, when it forms square planar complexes from the distorted octahedral complexes, the Z bond is not there. It is very much weakened and it is vanished there. It is ಅದು ಇಲ್ಲ ಅಲ್ಲಿ z axis ಅಲ್ಲಿ ಬಾಂಡೇ ಇಲ್ಲ, ಆದ ಕಾರಣ z orbital energy ಇನ್ನೂ ಸಹ ತುಂಬಾ ಕಡಿಮೆ ಆಗ್ತದೆ. So you can see here Z orbital energy is lowered. Again here also Z orbital energy is lowered because Z axis is removed. And this is the crystal field splitting parameter or the energy which can be calculated by this diagram. Now, what are the factors influencing the crystal field splitting parameter? That is delta naught, delta T, delta SP in square planar, delta T in tetrahedral. How can you calculate the crystal field splitting parameter, or how can the factors influence the crystal field splitting parameter? So, first factor is if there are different charges on the cation of the same metal. For example, you consider iron, ferrous, and you consider ferric. Ferrous is 2 plus and ferrous is 2 plus and ferric is 3 plus. Look at the delta naught value, crystal field splitting parameter. In the first case, ferrous case, it is 10,400. It is octahedral complex with the water as a ligand. Now, look at this value. It is 13,700. So, ferric value the crystal field splitting parameter is higher. What is the reason for that? When you have studied the Fajon's rule, isn't it? Here also same thing. See, when the charge on the central metal ion increases, the crystal field splitting parameter increase. So the reason for that is the Fajon's rule. If the higher oxidation state of the central metal ion is higher, the charge is higher, and it will polarize the ligands effectively. Ligand ಅನ್ನು effectively polarize ಮಾಡ್ತದೆ, so that the crystal field splitting parameter, or the crystal field, the energy gap between the split orbitals increases. The second one, different charges on the cation of the different metal. So here look at the different metal atom. One is vanadium and one is chromium. So in chromium case, it is more. Why? Because charge is more. As the charge increases, or the central metal ion oxidation state increases, the crystal field splitting parameter, the energy gap between the T2G and the EG orbital increases. So it is 17,400, whereas in the metal ion having lower charge, it is less. Then the third factor, size of the d orbitals. You look at the three example. One is cobalt, and down the group in cobalt it is 27. It is D7 system, and if you 3D7 we can tell. And rhodium, below cobalt comes rhodium. It is 3 plus. Cobalt is 27, and 3 plus means 3 electrons are removed. So from 4s 2 electrons, and 3d 1 electron is removed, so it becomes 3d6. Here it becomes 4d6, and here it becomes 5d6. As the size of the metal, central metal atom or ion increases, what happens? The extent of crystal field splitting increases. Why it has to increase? Can you tell me? Because when the size increasing, you know that metal d orbital, if the size is small, and if the size increases, this is 3d if I consider, this is 5d if I consider. 5d if I consider, the orbital is having is spreading its lobe farther in space. Farther in space means it is spread near to the ligand. As a result, the extent of bonding increases there. So when the lobe size increases, extent of bonding also increase. So as extent of bonding increases, you know that repulsion increases, and the splitting parameter also increases, and the energy, that is delta naught, also increases. So, as a result, the electrons in the 4D orbitals interact more strongly with the electrons in the ligand orbital. Therefore, crystal field splitting is more. Similarly, 5D orbitals are bigger than that of the 4D orbitals. So, 5D orbitals crystal field splitting is more because the size is more. As the size of the central metal ion d orbitals increases, crystal field splitting orbital also increases. Why it increases? Because the size of the lobe increases, so that they extend farther into the space. That means they will come near to the ligand orbitals, so that the repulsion of the electrons between the metal ion and the ligand will be more. You know that when the repulsion between the metal ion orbitals and the ligand orbitals increases, what happens? Splitting also increases. Splitting energy gap also increases. So crystal field splitting parameter increases. Delta naught increases. Then the geometry of the complex. You know that tetrahedral complex, the splitting parameters is very less. I already said what is the reason? ಯಾಕೆ ಟೆಟ್ರಾಹೆಡ್ರಲ್ ಕಾಂಪ್ಲೆಕ್ಸ್ ಅಲ್ಲಿ ಕ್ರಿಸ್ಟಲ್ ಫೀಲ್ಡ್ ಎನರ್ಜಿ ಕಡಿಮೆ ಆಕ್ಟಾಹೆಡ್ರಲ್ ಕಾಂಪ್ಲೆಕ್ಸ್ ಗೆ ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ? Because Tetrahedral complexes have only four ligands. When the four ligands are interacting with the metal electrons, the repulsion parameter is less. So repulsion is less. Repulsion is less. Whereas in octahedral complex there are six ligands, so repulsion is more. You know that repulsion is more means energy also more. So repulsion is directly proportional to the energy. So these are the factors. Now applications of crystal field theory. So one can determine the color of the transition metal complexes. So color can be directly proportional to the crystal field splitting parameter. So crystal field splitting parameter, as we saw, as the central metal ion, the size of the d orbitals as it increases, crystal field splitting parameter also increases. And also we have seen the charge, central metal ion charge increases. You know that when the charge central metal ion oxidation state increases, the central metal ion becomes smaller in size. You know that Fajal's rule, smaller the size, it will polarize the ligand orbital effectively. As a result, the distortion of the metal orbital ligand orbitals takes place and covalent nature increases. You know that as a result, the energy also increases. So when the central metal ion charge increases, splitting parameter increases, energy increases, and as energy increases, you know that it is directly proportional to the color of the transition metal complexes. Now we have to see how it is related. The splitting parameter and the color of the transition metal complexes are related. Now, if you see transition metal complex ions whose central metal atom contains partially filled d orbitals are usually colored. Why? We know that it is dd transition which is taking place. What do you mean by dd transition? So dd transition is the transfer of electron from the T2g orbital to the Eg orbital. So that is called as, so when the white light is fallen on the complex, octahedral complex of the transition metal ion, the ion or the compound absorbs some portion of the white light and the remaining portion of the white light is transmitted. So you see here, I am taking a beaker full of solution. Now, when the white light is passed, you know that white light, when it is passed, it comprises of seven colors. Suppose that one color is absorbed. Suppose that one color is absorbed, that is green color is absorbed. So the resultant color is subtraction of the green color. Remaining color is complementary color is seen. If you see the green color, when it absorbed, the green color is removed from the seven colors, and the complementary color which is seen is not green, which is purple in color. So you see that here green color, when it absorbing, the color which is seen to our eye is violet color, purple color. So you see that when it absorb violet color, we see the complex as green color. When it absorbs blue color, you know that this is blue color, and the color seen to our eye is yellow. Like that, complementary color is seen. So, how can we explain the purple color of the octahedral complex by the dd electron transition? You know that in titanium complex, that is hexa aqua titanium 3 plus complex, it is octahedral complex. How do you say it is octahedral complex? Because there are six ligands. When there are six ligands, it is octahedral complex. And titanium is the central metal ion whose charge is titanium 3 plus. You know that titanium is 22, and it is 3 plus means 3 electrons are removed. 22 means it is argon 3D, 2 and 4s 2. So when you remove This is titanium. Titanium 3 plus. In this complex, titanium is 3 plus ion. So when you remove 3 electron, the electronic configuration becomes 3d1 4s2. That means 2 electron from 4s orbital and 1 electron from d orbital is removed. So this is the electronic configuration. D orbital is having only 1 electron. So when 6 water molecule approach titanium ion to form the octahedral complex, the 5 d orbitals of the titanium, the 5d orbitals of the titanium ion is split into T2G and EG sets. Remember that when the white light is fallen on this particular complex, these are the changes taking place. The d orbital of the titanium 3 plus is split into T2G and EG set of orbitals. And that phenomenon is called crystal field splitting. We have studied, just now we have studied crystal field theory applied to octahedral complexes. And T2G set of orbital is having lower energy, isn't it? That is what we have studied. Which are the T2G set of orbitals? Can you tell me? DXY, DXZ, and DYZ. They are having lower energy. Which are the EG set of orbital? Can you tell me? Dx square minus y square and dz square orbital are EG set of orbitals. So T2G set of orbitals are dxy, dxz and dyz, which is having lower energy. Why they are having lower energy? Because octahedral complex, these three orbitals are in between the axis, isn't it? Dxy, dxz and dyz orbitals are in between the axis. But in octahedral complexes, ligands are approaching the metal ion from x-axis, y-axis and z-axis. Since these orbitals are in between the axes, they are experiencing less repulsion and they will be having lower energy. E.g., dx square minus y square and dz square. These two orbitals are on the axis and they are experiencing more energy. So therefore, the d1 electron resides at the T2G set of orbital and Eg remains vacant. So the lower energy occupies the d1 electron of the titanium 3 plus. And when white light is allowed to fall on titanium 3 plus ion, the ion absorbs green radiation. So white minus green is violet color. The absorption of the green light takes place at the wavelength of 400 nanometer. So the energy associated with 400, you can calculate what is the relationship between energy and wavelength. E is equal to h nu h nu. E is equal to hc by lambda. So wavelength is inversely proportional to energy. So by this equation, one can calculate, if you know the wavelength, one can, H is Planck's constant, C is the velocity of the light, energy can be calculated, is coming to be 239 kilojoules per energy. This energy is close to crystal field splitting energy, that is delta naught. This energy is close to crystal field splitting energy, that is delta naught. So that is why the electron present in T2G orbital absorbs 239 kilojoules per mole of energy and it is excited to occupy the vacant EG orbital. So that is why we can see purple color. It absorbs, that 500 nanometer, it absorbs green color and it to our eye, it appears as purple color. Similarly, here also you can see hexacyano-cobalt complex and hexa-ammonia. You know that this cyanide is strong ligand, splitting parameter is more, delta naught is more. So the wavelength it absorbs is lower wavelength, higher energy. You know that higher energy, when it absorbed, yellow color is seen to our eye, complementary color is seen to our eye, and ammonia is little weaker compared to that of cyanide, and it absorbs blue green color, and orange is complementary color which we can see. And here nickel hexa aqua nickel complex, if you see, water is a weaker ligand compared to that of ammonia, so water will absorb red region, higher wavelength, and green color is seen to our eye. Complementary is green. To red, complementary is green. Then hexa ammonium complex, the yellow color, orange yellow color is absorbed, and the blue color is seen. And if you see copper complex and zinc complex, Cu plus and Zn2 plus, it is having D10 configuration. You know that completely filled, they are usually colorless. They cannot have the DD transition. D to G to Eg transition is difficult because of the completely filled electronic configuration. Here, one more example, if you see water ligand, ammonia ligand, and ethylene diamine ligand, if you see, you know that ethylene diamine is the strongest among all, and it is highly colored complex, strongly colored complex. Then ammonia, then comes water here, which is having weak ligand and color is less. Thank you. I hope you have understood crystal field theory, which is applied to octahedral complex, tetrahedral complex, and square planar complex. And if you see all the three complexes, crystal field splitting parameter for square planar complex is highest, then it is octahedral, then least is for tetrahedral. Why tetrahedral complex? The splitting parameter is less than that of octahedral, because in tetrahedral only four ligands are there, and those ligands are not, they are in between ligands, and they are not directly coming in contact with the metal ion orbital. So repulsion is less. Whenever you know that repulsion is less, splitting parameter is less. So thank you.
ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು ಮ್ಯಾಮ್. ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ಅದು ಕ್ವಶನ್ಸ್ ಇಲ್ಲ ಮೇಡಮ್, ನೀವು ಕೇಳ್ತಾ ಇದ್ದಾಗಲೇ ಅವರು ಆಕ್ಚುಲಿ ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ಅವ್ರು ಆನ್ಸರ್ ಮಾಡ್ತಾ ಇದ್ರು, ನೀವು ನೋಡಿಲ್ಲ. ಹಲೋ
Yes, I'll see.
ಹಲೋ
Hello.
ಥ್ಯಾಂಕ್ ಯು ಮ್ಯಾಮ್.
Thank you, sir.
I would like to thank you immensely for delivering a very informative and insightful talk on crystal field theory of KST and myself. Once again, I thank you, ma'am.
Thank you, sir.
ಸೊ ಇಂದಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಹಾಜರಾಗಿದ್ದ ನನ್ನ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರಿಗೂ, ಉಪನ್ಯಾಸಕರಿಗೂ ಮತ್ತು ಶಿಕ್ಷಕರಿಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳನ್ನು ಹೇಳುತ್ತಾ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವನ್ನು ಮುಗಿಸುತ್ತಿದ್ದೇವೆ. ಕ್ವಶನ್ಸ್ ಏನಾರ ಇದ್ರೆ ಮೇಡಮ್, ಫ್ಯೂಚರ್ ನಾನು ನೆಕ್ಸ್ಟ್ ಫ್ಯೂ ಡೇಸ್ ಅಲ್ಲಿ ನಾನು ತಮಗೆ
ಅವರು ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ಆನ್ಸರ್ ಮಾಡಿದ್ದಾರೆ. ನಾನು ಕ್ವಶನ್ ಗೆ.
Yes. Okay. Once again, thank you, ma'am.
Okay, thank you, sir. Thank you.